Oh,
I,
damn, I thought till 97 maybe you could get something in pop.
nah, man. If you have 98, you can do something. Like, you can go for, you can go through IELTS, and then you can like maybe apply for ENPC or something like that.
Okay.
And plus, the thing is, they don't participate in a lot of competitions. I wa- like the college which do is like PCCOE and MITWPU and COEP. The COEP is like the far-fetched dream right now. Not possible, man.
CMP is impossible. That is like
To
literal top university.
99.8. Yes, 99.8. Even if you get 99.8 right now, right, there's no chance to get CS, man. 0%. You need 100 percentile, man. Or you need to be like
What?
in category. Yeah.
Or
Like
top
seriously,
60 on
like,
the merit list.
yep.
Okay, what college
And
was
like
that?
top 60, COEP.
Oh,
It's pretty good, I guess. Pretty good for to be told top college in Maharashtra, I guess.
yeah. What about MST CET? That has pretty good college as well.
Yeah, no, I am taking through MSc right now. So they have the best colleges are COEP, then PICT, then maybe Cummins, because like that's only for women. They have high cutoff, and
Yeah.
after that, it's called this PCCOE, and then VIT, and then Divai Patil Akudi. The reason why I'm taking Divai Patil Akudi is that it's close to my house and like not like it's pretty good. VIT, if I go for VIT, there will be the up down of like for me to go there, it will take 2 hours and almost like per day I will travel for 5 hours. And my parents are not allowing me to like take a hostel there and live alone.
Oh,
Yeah, sad.
sad life.
Yes.
I mean, I've been living in hostel since 3 years now.
Yeah.
I did my 11th and
So
12th in
jealous, man.
hostels there. Bro,
Oh,
if you did go to hostel in
hostel.
11th
Yeah.
and 12th,
Like,
it would have been
huh.
traumatic.
Yes. Like you did it for like preparing for J something like that or no wait, did you went to Kota?
No, no, no. Uh,
Oh,
in Odisha, we have the main capital city of Odisha is Bhubaneswar. I had my 11th and 12th there. So, like, do you know about Fiji?
yes, yes, yes. It was
Yeah,
very popular in Maharashtra as well.
yeah. So I was basically the last batch of Fiji.
Nah, basically
Before,
same, but in Allen.
oh, after that, the entire Fiji controversy happened, and I guess Fiji just got bankrupt.
Yeah, yes, yes, yes. It was running like when I was in 11th, it got bankrupt or something, and they just closed it. They closed the entire thing.
Damn.
And the people who were studying Fiji, they all came in Allen or something.
It feels as if like wherever I go, the place just shuts down at this point.
No way.
I'm like the guy from uh, India's Got Latent.
Which one? Which one?
The guy that
Oh,
says
the
that
beer bicep. Yes, yes, yes.
no, not
Beer
beer
bicep
bicep.
or something.
It was a person who came to India's Got Latent and he said that wherever he goes, the entire place shuts down. And then when he visited India's Got Latent shut down as well. He visited Indigo, and then Indigo shut down as well.
Oh, crazy. I didn't know that. Nice, nice. Respect, bud. Aura.
Yeah.
Yeah, I know this. I saw that on Instagram.
Yeah. Can you guys see my screen?
Yes.
Yeah. So I'm just gonna quickly go through the initial sections of the video. Like the video initially discusses why legged robots are so special in research discussion. The main reason being legged robots can just traverse various spaces without having to like care about their environment, whereas robotic cars or even drones need like a pre-specified environment in which they move. Like robot cars need
Hmm.
roads and drones need air clearance, whereas legged robots can just go wherever they want. And again, they have better strength capabilities because they can rely on friction, which these wheeled robots can't. So the task in this research paper dives into is we have the prerequisite we have is the kinematic and dynamic models and properties of the robot that we know beforehand. We know the goal of beforehand, like where we want to move the limbs of the robot, and but we have no idea about the terrain. The only thing we know about the terrain is that it's solid. That's it. uh, in order to move the robot, we need a motion plan. A motion plan is nothing but the like the commands to move each joint with the parameters to be position and speed. Like with these two parameters you can basically uh, control the entire robot. You could specify that this particular joint needs to move at X position with Y speed. That's basically all you need. And this poses a problem because there are basically an infinite number of solutions to do that. Like you could just stomp the feet of the robot, you could take a detour, or you could have like millions and millions of calculations of possible like possible values for these two parameters, right? uh, Sorry. Yeah. So what we generally want is quote unquote the best solution to the motion plan. And what I mean by best solution is, let's say you want to move, you want to make the robot walk from point 1 to point 2, then uh, it should minimize the like the movement of its limbs. The movement should be efficient in terms of distance, in terms of time. It should take any detours in case there is an obstacle on the way, that sort of things. Generally that would be like pretty easy because we already have that in the industry for a long time, but they are pretty much always specified for a specific environment. Like I think it will be better if I draw this out. Yeah. So we have a multi-legged robot, and we basically have an unlimited amount of like possible position on where these joints can be. This joint could technically be right here as well or here as well, but we need the most optimum position and speed to put this robot joint, and it's typically easy to do so because there's a lot of research on that, but it's all done in controlled environments where we know the friction coefficient for the surface, where we know how the terrain is, like if the terrain is flat or curved, etc. However, in real life scenarios, the terrain is never regular. There are obstacles, there are like irregularities in the plane, and then the friction coefficient might change midway, right? And if we were to optimize this motion in the conventional way, we would just take uh, like some function z, let's say, and it would have some parameters which would be uh, like we want to optimize the position and speed, right? So let's just take those two for now. I haven't read if this is the optimization function. I'm just taking this as an example, but what I want to focus on is this thing. How do we get these weights? We get these weights depending upon these parameters, like the friction coefficient, the flatness of the plane on which the robot is standing, etc. We can do that for a predefined plane, but it's basically impossible to do that for a random plane because we have no idea about the friction coefficient or how the plane is, right? So we need to formulate some method that's gonna help us like create an optimum solution without the need of these weights. So you guys remember basic optimization theory, right?
Actually, no.
Uh,
We just know, like, means I just know basic from like class 11 and 12. So
yeah, yeah, yeah.
Newton's law, maybe
Uh,
work and energy, those stuff.
like, do you remember in 10th standard maths where we had some function, let's say 2x1 plus 3x2, and we had some constraints upon that, and we made a graph where we would plot these constraints, find its
Okay,
area.
right.
Yeah, you remember that, right? And then
Yes, yes, yes.
we used to get like the few corners from these, and then we would put these points in the function that we want to maximize or minimize,
Oh,
and
yeah,
we
yeah,
found the
yeah.
answer.
Right.
Yeah. What about you, Izito? Are you with me? Yeah, nice. So yeah, as I mentioned, we have no idea about these weights because the plane is absolutely random and we have no way of formulating these constants, right? So what the paper proposes is that instead of uh, like having a feasible region and then we put these sort of points into this some equation we want to maximize, what the paper proposes is we model the optimization problem just using constraints. So what does that mean? So basically we make lots and lots and lots of constraints to the point that there is only one single possible solution. This is what the paper proposes. That's what I have understood till now. So if we manage to do that, then we would just have a single function that we can use in order to make any legged robot work in any environment, and that's absolutely huge. So that's why uh, ETH Zurich, you might know this, ETH Zurich is one of the best research universities in the world, and they made a tutorial for this specific research paper 8 years ago. Imagine, they made all this shit 8 years ago. Imagine the things they are working on right now.
Crazy, bhai. Crazy.
Yeah, yeah,
8 years ago, damn man. Like before the pandemic and all. Damn, bro. Respect.
exactly. Like, imagine this before ChatGPT. Yeah, so initially they took a generic equation, like this is just a way to denote a general optimization problem, like the cost function that you wanna minimize, and then uh, like few constraints which are gonna make the feasible region. But then they realized that it's impossible to figure out the weights for every environment on the fly, so they ditched the entire cost function, and then they focused on making absolute constraints that are going to yield only a single solution. Yeah, so these are basically representations of the constraints. So this is a constraint, like this is the plot for one constraint, this is the plot for another constraint. So as you might remember, the feasible region lies in the intersection of all of these constraints, and finally we'll have only a very small area. So I guess for the rest of this part, all they do is, in the video, all they do is make various techniques to find this area more efficiently, and I think that's a topic on its own, so I'm not gonna go through it too much. But if do you guys wanna know a little bit about it?
Yeah.
So basically, if we are making an algorithm that's gonna find the solution, so instead of it scanning every possible point, we just uh, let it scan the probable area. Like, we know that the intersection's gonna lie somewhere around here, so we only search in this space for the intersection. Does that make sense? In case you did not get it, if we are making an algorithm to find the intersection of these constraints, so instead of searching all around the graph, we just search at a very small area to make the algorithm more efficient. Basically, it has less area to search, so less time. And then he starts with the serious shit, which I guess we'll need this session and a lot of concurrent sessions to understand, like, these sort of things. This is this comes under robot dynamics, Newton Euler equation, which describe like forces that are playing on joints of the robot and things of that sort. So these these 3 minutes of video is about a month of our time, and then this section of video is another month of our time, and then this will become really easy. Anything above this point should be pretty easy if we like focus on slowing down on these sort of basic things. So in order to understand the kinematics and dynamics of robots that are going to be used in this video, like the dynamic model of the robot and all the weird shit and symbols that are going on in this, we are going to follow a book called Intro to Robotics by Saeed B. Nico. I think I have this shared in intermediate mega thread. I hope so. I think Justin shared it, or I might have shared it as well. Yeah, here it is. So, in case you don't find it, I'm gonna share it in this as well. Oh. So if you guys want, you can just open this book on the side and just listen to me if that's more comfortable. And I'll post any notes and updates on my GitHub repository, I guess, and I'll be making the notes simultaneously in the session.
Hi, so my PC just crashed. I restarted it. So what happened?
Oh,
Could you
uh, what was the last thing you heard from me?
you are teaching about the actuators, the target robotics, like about putting constraints.
Yeah.
Only a point is in the constraint, so
Yeah.
that point only becomes the like output.
Solution. Yeah.
Main output.
Okay, so you might have missed a shit ton. Wait. Did you see this image?
No, you can just resurface. You just close that one.
I will. Yeah, I'll upload them. But Did you see this particular image of the constraints?
Yeah, I saw this one.
Okay. So you haven't missed a ton. So basically, what I told next is that uh, other parts of the video discusses the dynamics and kinematics of this particular robot that they are using, and then it talks about optimizations. So basically, covering this 3 minutes of the video is gonna take about a month of our time, and then another month to cover optimizations. However, anything above that, like from this to this, is gonna be pretty easy. The only hard thing is getting started on these areas. If we take it slow on these areas, then I guess we can just speed up through the rest. Yeah. So there are like a load of weird symbols and concepts that are going to be used, like Newton's Euler equations. Like even I haven't heard about it ever. So we'll follow a book called Intro to Robotics by Saeed B. Nico, which I have shared in my post in devlog, or you could just hop over to intermediate megathread. I have it in there as well. uh, I would hope that you can open the book on your side if that's comfortable, and you can just listen to me talk if that's more comfortable to you. Do whatever you want, I guess. uh, yeah. mm, what was I Biniko? Did you get the book I sent?
Yeah, got it here on the intermediate megathread.
Nice.
By Saeed, right?
Yeah, by Saeed. Uh, Also, I have mapped out the exact things we need to cover, so we don't waste time discussing the initial theoretical bits. Like, I have covered the basics, like, I mean, advantages and disadvantages of robots, which I think you already know, and basic robot components. Uh, if you really want to read about it, then you could just look at my notes in the GitHub as well. We, I've covered the initial basics, basically the motivation to robotics, I guess, in this first file. And then in the second file, I have covered the actual mechanics, and this is what I'll be adding to. So for the initial few bits, you could, like, I'll just refer to my notes instead of the book because I have just compressed it down anyway. We'll divide our study of robot mechanics into two parts. One is kinematics and another is kinetics or dynamics. Kinematics is simply the study of position and velocities, whereas dynamics introduces forces as well. For robotics, we need forward kinematics as well as inverse kinematics. What forward kinematics means is determining where a particular object, let's say a robot's hand, will land finally once all the joint variables are known. Let's say let's say there is a robotic hand, and let's say there is a robotic hand, and we know the exact exact configuration of all of these joints, then after knowing the configuration of all the joints, determining the position of the hand would be called forward kinematics, whereas determining the joint positions in order to move the robotic hand to a particular position would be called inverse kinematics. And as you might have already thought of, forward kinematics is pretty easy because we already have an intuition of forward kinematics from our 11th 12th standard. Like if I move this joint by 30 degrees, this by 20 and this by 10, then it's pretty easy to calculate the position of
Hello?
this robot. Yeah.
Uh, like like Neil is having some problem, I guess. Like he's saying the stream has stopped or
It's solved
something.
right now.
Nice, nice.
Uh,
Continue, continue.
uh, is the same problem with is it a thing on my end, Neil?
Mm,
no. It's solved now. I think it was from my end.
um, okay, so
It's solved now. Let's continue.
yeah, in case you did not get it, forward kinematics, like we divide our study of robot mechanics into two parts: kinematics and dynamics. Kinematics deals with positions and velocities, while dynamics introduces forces on top of everything that kinematics does. And again, we divide kinematics into two subparts: forward kinematics and inverse kinematics. What forward kinematics means is we have the properties of all the joints. Let's say we move the joint by some degree, this by some degree, and this by some degree, then we'll find the final position of the end, like the end effector or the hand of the robot. This is called forward kinematics. Have uh, if we already have idea about the initial parameters of the joints, and then we can find out where the robotic hand will end up. That is called forward kinematics. And if we had to inverse that, if we had to find the joint positions by directly by the intended position of the robotic hand, I guess. If let's say we wanted to move this robotic hand from point A to point B, then the study that requires finding out the position of the joints of the robot is called inverse kinematics. So uh, I think forward kinematics, mm, for forward kinematics you might have a bit of intuition from 12th standard. Like it's
yeah,
as simple,
vectors and all.
yeah, like moving this joint by some degree, this by some degree, this by some degree, we can find out the position of the robotic hand. And if we wanted to inverse that for inverse kinematics, we would need to find the joint angles in order to move this robotic hand from point A to point B. Inverse kinematics involves a lot of guessing and intuition, whereas forward kinematics is pretty straightforward and it has rules and formulas that we can directly use. That's why inverse kinematics is an issue when we deal with things like moving robotic arms, or in our case, in our research paper, moving the limbs of the multi-legged robot. Inverse kinematics is pretty damn hard, and that's why we need a shit ton of theory for that. That's why this book has these many pages.
Crazy. You just like summarize the first chapter of that book, man.
I mean, the first chapter is basically
Yeah,
applications and shit like that. If you wanted to know, then you could just read my notes, or I don't think there is too much theoretical, or uh, I mean, yeah, these things aren't
Uh,
directly related to
Sandeep,
us. Yeah.
if you don't mind, can you recap what's like in short, even within 1 minute, what's happening right now or what has happened?
Wait, did Neil's PC crash again? I think
yeah.
Neil. Oh shit.
He just left, I guess. He was having some issue, I guess.
Uh, okay. So, Masao, we are reading a research paper which deals with the trajectory optimization of multi-legged robots. If I simplify that, then in order to make any multi-legged robot go from point A to point B, we have an infinite number of possibilities, right? We could uh, make the limbs of the robot just stomp on the ground, or we could design a particular trajectory. However, there are a lot of constraints as well. What if the road is not regular, or what if there is an obstacle on the way? Then we need to detour the entire robot. And what that means essentially at a lower level is we need to have a plan of where each joint of the robot has to move, and that essentially boils down to an optimization problem. Do you have any idea about optimization problems?
Uh,
Sorry.
like means my college has started teaching it, but I have been like not going to college
Okay.
from 2 weeks, so I'm pretty far back in that sense. But yeah, I have like generally like Joe like uh,
We remember the basics, right, from 12th, where we had to draw a graph in order to, like, we had a lot of constraints, and then we found a feasible
yeah,
region.
I'm on that, I guess. Like you
Yeah.
can see the um, syllabus we have.
Yeah. I mean, we all are basically on that level, so we'll, I guess, grow together. Uh,
What's your syllabus, if you don't mind me asking?
for me, for my university, we started with the graph method, and then we in like the last class we started using the analytical method. Basically, we had a matrix which we used to solve an optimization problem. Like, we in our
Mm-hmm.
class we are just dealing with linear optimization problems for now, and we'll deal with non-linear ones later on.
Oh,
It's included in the syllabus.
okay. Yeah. Yes. I'm also on that level too, I guess. Linear programming problems. There are different methods, right?
Yeah.
Simplex methods, big
Yeah,
N
yeah,
method.
yeah.
Yeah. Okay. And you said like your professor like had some experience in creating this with robotics. What was that?
Yes. I just quickly searched up her on LinkedIn, and I did see that she has previously worked on localization and mapping, I think. And I think that should be enough, because just after talking to her for a few minutes, it was apparent that she has some knowledge about robot mechanics as well, and I think that's a plus.
Great.
Yeah. So, uh, in every optimization problem, we generally have a function to optimize, and then we have some constraints, right?
Yeah.
And the optimization, the cost function looks something like this generally.
Mm.
And these weights, in our
Yeah.
context of the research paper, depend on the surface. The surface is uh, friction coefficient, the irregularities in the surface, etc. So if we had the environment preset, then we could just find these weights. But the research paper is trying to find a single formula, some single function that's gonna enable us to use our multi-legged robot in any scenario. So the paper is trying to develop a formula for any multi-legged robot to enable it to traverse in any sort of environment. Hello.
Yes.
Yeah. So
Yeah, yeah, I can hear you. Yeah.
we'll have constraints in such a way that there is one or a very few possible solutions to this problem. Essentially, we need the position and the velocity of the joints at the end of the day, and we'll put some constraints in such a way that we wouldn't need to use this cost function. Like, if I quickly show you the video with the bro.
Crazy.
Yeah. So
Yeah, brother, use Bay or something. Like it blots the ad and all.
I just like Chrome's this feature for Google Lens. That's why I'm using it. That's the only reason.
Crazy.
Yeah. So the paper implements constraints. Like, this is the graph plot of one constraint. This is another, and this is another. And then this area is the feasible region, or the intersection of all the constraints. And we make the constraints in such a way that there are either one or a very few possible solutions for the position and velocity. That's what we are trying to work out. And in order to actually do this properly, we need to read a lot about these sort of equations, which are covered under kinematics and dynamics. Like, currently, even I have zero idea what all these mean. Like Newton's Euler equations, I have never heard about it. So basically, these few minutes are gonna take up a month of our time, and then this optimization thing is gonna take up another month of our time. But then anything else after that should be pretty smooth.
3 months.
I guess I have like the stuffs you mentioned in my syllabus. Let me check if I really have them or not. I mean, if I have them, I'll try to speed run them.
Yeah.
Cool.
And I'm talking to my professor about some book recommendations. If she can, then I'll share the book as well.
Yeah, please do.
Yeah. And instead of doing this entire big thing at once, we'll take up some mini projects. I have some mini projects planned that's gonna use up some of the concepts that we learn on the way, so we don't get exhausted during this.
Like building a project is not that simple, brother. Like, for example, I was trying to build a self-balance robot, but the thing was, I need MPU 6050. I tried to buy it from a local shop, but
Yeah,
I got scammed twice. Like the
bro.
first thing, like first time it was my fault. I did the soldering by myself. That
Yeah,
was the main issue, I guess. It didn't work. Second time I did the soldering by through a professional. The chip was fake, man. Like he said, one of 200 will be fake. Like I have to go to him and say कि भाई तूने scam कर दिया पैसे निकाल.
I mean, I don't really trust offline shops for this sort of things because all they have are
Yeah.
clones.
No,
You
even on Amazon, like if you search MPCC, half
even
of the
am
product like
Yeah,
have.
even
Yeah.
Amazon, it's full of fake shit. I think robo.in is something I trust.
Yeah.
Yeah, robot is robot.in. Yeah, they're pretty good.
Nah, actually, I tried to buy it from Robotrades, but thing was, the review says like half of them said that it is fake, and like if you return them, they will like
Yeah,
just forward it. Like they will say you will get the MPU 6050 after 1 or 2 months.
bro.
After returning and all that, like no refund, no such thing. If you get lucky and you get the genuine thing, then yeah, you are lucky, man. That's why I'm like waiting for someone else to buy MPU 6050, and if he gets the real one, I'll just buy from there.
Yeah. By the way, don't worry. This mini project is gonna be a simulation, so you won't need to buy anything.
Oh,
Yeah.
yes,
This
pretty
in
cool.
Yeah. This is basically implementing the motion controller of generic like, uh, robot car, I guess. That will use up a lot of physics that we are gonna learn.
Nice.
So
Let's do. Hmm.
let's speed run through the initial few things. Uh,
I don't know, like basic of forward and kinematics and inverse kinematics. I was trying to watch some videos. I
yeah,
have little bit idea about how to do all the equation solving and all that. But
nice.
like the more I try to do it, the more I realize that I don't know anything.
Yeah, even for me, I know the formulas. I have a way to memorize them, but when I talked with Justin, I realized that I have no idea how to actually derive those formulas. That's something I need to work on because if I don't work on that right now, then I'll be absolutely fucked if I read an actual research paper in the future.
Yeah,
Hmm.
Yeah.
like you
So
need basics, yes.
uh, I'm gonna speedrun some basics. As you might already know, a frame is just the coordinate system, like the the three coordinates x, y, z that we can just put into some object to track it. So the world frame in this instance would be a reference frame that we are going to use as our default, and if I ever refer to the frame of the end effector, that would mean the coordinates of the end effector, and so on and so forth. And after that, these are just basic like matrix representations, I guess. In a few places in the book, you might see this additional variable called w attached to this vector, like any sort of vector. If you see another variable w attached at the bottom, you need to realize that this is just a scale factor. So the actual variable is this, the actual vector is this multiplied by the scale factor. That's it. And then uh, as I was talking about the frame or the coordinates, like yeah, this is the coordinates of the end effector or the frame of the end effector. We can represent the frame of anything as a matrix as well, and this is going to be very helpful later on when we transform a frame. So this is something really cool. We later on we'll have a single matrix that if we pre-multiply it to this frame, then we can move the end effector or any joint to any position that we want. So let's say we wanted to move this at another point, just multiply with a single matrix and boom, it reaches there. That's it. So
Yeah.
uh, the frame is represented by three vectors, obviously three axes called NOA, and you represent the vectors vertically and make this into a matrix. That's it. And let's say we wanted to represent uh, the frame of the end effector of a robotic arm with reference to the world frame. How would we do that? So we would simply take the initial frame, which would be the frame of the universe, the universal frame. We would take the universal frame and then write another vector that's joining the origins of the frame we want to represent. So if that got too
Mhm.
overcomplicated, uh, this is the world reference frame, which we need to uh, take in reference, I guess, like the thing we are gonna taking in reference to represent this frame. So this is basically considering that we want to represent this reference frame relative to this universal frame. Let's start with that. And the way we do that is we make another vector joining the origins of the world frame and this reference frame, and then we write the world frame and then the vector, and that's it.
Yeah. Yes.
So let's say this frame moves somewhere else, that would mean the position vector would move along with it, and hence the matrix would change accordingly. After this session ends, I would recommend you to try out a few examples from the book. uh, I have solved a few. If you want to try them out, you could do as well.
Yeah. Like I did so like I completed chapter 2, so I have little bit idea of this.
Yeah. Uh, oh wait. Okay. I might have said something wrong here. So this, like, wait. this part of the matrix, the NOA, is actually the reference frame, not the world frame. Yeah, I was pretty wrong there. And we are just writing the vectors themselves in reference to the world frame. So the angles of the vectors are going to be measured in reference to the world frame. That's how we take the world frame into consideration. Just to summarize, in order to write the matrix, in order to represent a reference, in order to represent a frame in as a matrix relative to a particular reference frame, or in our case a world frame, we simply write the matrix that we want to represent and then a vector connecting the origins of both the frames. That's it, as simple as that. Then once we have already learned how to represent frames, it should be pretty easy to learn the representation of rigid bodies. So the position and orientation of the rigid body would be very similar to the representation of the frame, because we can just attach a frame to the rigid body. Yeah. Since the object is permanently attached to this frame, its position and orientation to the relative frame is always known. So in order to represent a rigid body, let's say a cuboid, let's say a cuboid in 3D space. Ow. In 3D space, what we do is simply attach a reference frame to this and then represent this frame in the form of the matrix that we saw. We also have a concept called degree of freedom, which you might have learned in chemistry in 12th standard. So
Yeah.
the degree of freedom basically describes the minimum number of parameters in order to describe the position and orientation of a robot or any object, essentially. So let's say that let's say we are working in 2D and we just need to represent this point. Then what we need is simply two variables, x and y. Therefore the degree of freedom of this point would be 2. Similarly, if we wanted to represent a shape, let's say a rectangle, in a similar manner, then apart from the two variables x and y for the position, what we would also need is the orientation, because I can just wait, how do I rotate this? Shit. Legitimately, how do I rotate this? bro. Control T. Yeah, so we could rotate it as well. So apart from the position, we also need another variable, let's say theta, for its orientation in 3D space. Similarly, for a 3D object in 3D space, do you guys want to guess how many parameters we need in 3D space? Let's say there is
Four,
a
4 or 5. It depends.
mm,
Like, it's a 3D object. We at least need four, I guess.
yeah,
Like
it's a
X, Y, Z,
3
and like theta.
yeah, it's a 3D.
I guess it would need five, maybe 5 to 6.
Yeah, it's a 3D object that's just floating in space.
Yeah, I mean one would be two.
Four.
Let's see.
Yes, four should be correct now. Please be four.
I mean, for the position already, we need at least
Yeah,
3, right?
6.
For X, Y, and Z
Yes.
for the position. What about the orientation? What do you think?
Yeah.
Oh,
Think of the ways that
but we need to.
we could rotate this
Oh
cube
shit,
around.
5. Yes, yes.
Are you sure, bro?
Uh, that
I
I
mean,
Oh
you
damn,
I
could
don't
one.
think
One, two.
think of the
Actually,
maybe
independent.
five.
okay.
So, do I have
Like
a
it
final
can rotate
answers?
a lot of ways. It's again.
Think of the minimum number of variables that you need to describe its orientation. So, the minimum number of axes it needs to rotate about independently, that is. So, rotating it diagonally would just count as rotating it like this once and then like this again.
Plus,
So,
I
that
guess.
doesn't count.
2. If negative is also considered here, like negative theta is also considered here. Only two
Uh-huh.
axes.
Mm-hmm. I mean, it's
Uh,
best if I show this to you in Blender, because Blender is great at visualizing this.
It should be such like. Uh,
You can rotate independently about 3 axes actually. One about the x-axis, one about the y-axis, and another about the z-axis. And anything in between, let's say a diagonal rotation, is simply the combination of these.
then total sets. Like 3 for like X, Y, Z, and like 3 for like H theta, Y theta, and Z theta.
Yup.
I'll be back in a second.
So in total, we need 6 parameters.
Yeah.
Therefore, the degree of freedom for a rigid body is actually 6.
Pretty cool. Like मैंने यहाँ तक किया था, मुझे यहाँ तक पता है, but still मैंने mess up कर दिया.
I do have another uh, like mechanism in case you wanna use your mind again, just for fun. It's nothing
Yes.
related to our study.
Yeah, chillega.
It's called 4 bar linkage. It's from a book I was reading recently. Uh,
What bar linkage? Okay. If it's 2D, then 3. Oh, bar linkage.
this is a 4 bar linkage. So this, like, both of these are fixed to the ground, so these do not slide. These are absolutely fixed to the ground, and all of these three joints are connected. All of these three links are connected by joints. So a joint here, a joint here, a joint here, and another joint here. So think, how many parameters, how many minimum number of parameters would you need in order to describe this mechanism?
Well, okay, so like basically 2 point fixed है bottom के, right?
Yeah.
So you need minimum like 2 point इसके लिए, like जो third number था है, जैसे दोनों points के लिए दो दो लगेंगे, यानी कि 4 तो वहाँ पे हो गया,
Wait,
and
wait,
one
wait,
for
wait,
the
wait, wait, wait.
degree.
If you already know about this, then you do not need another parameter, right? The parameter is a variable, so if you tweak the parameter, then the robot's gonna change. But in this case, it's already fixed, so we do not need this. So if I fixed the cube in my previous example about an axis, then I wouldn't need another parameter for that. Does that make sense?
Kinda, I guess. Like I know what you're trying to say. Okay, it doesn't need one more. Like you still need a parameter for like the degree. Like for example, uh,
Like for
one,
this,
right? Uh,
I think you are. Uh, yeah. So, I mean, you could take your time and guess.
like see. We don't need a parameter for like this, right? Like the coordinates, we don't need coordinates. We
Yeah.
only need like degree.
Yep.
Uh,
Absolutely.
so so I will guess one or two. Like if we know degree of one thing, we also know the degree of another thing, right?
Yep.
One.
Yes, that is correct.
N- Oh, why not two? Uh,
It's one.
like see, we can like no, like 1 2 we can do for we can like have 1 degree, but what
Yeah.
about like 2 3 and 3 4? Right? What about that?
Let's say you change the angle of link 2. What do you think is going to happen in link 3 and link 4? Are they independent, or are
Oh,
they dependent on this link? If you move
yeah,
this link, then these are gonna move in a
yes, yes,
planned
yes,
fashion.
yeah. Like if we move one thing, the all will move. Yeah, they will say yes, yes. I totally get it now. Oh,
Exactly.
nice. Thanks, man. Like this concept is clear now. Thanks, man. Crazy.
This wasn't even related, it's from a book called Design of.
Crazy, man. Like actually बहुत अच्छा explain किया आपने. Thanks. Seriously.
None of my roommates got this on the first try, by the way.
Ah, ouch, bhai. Nice. Not the smartest, I guess.
I mean, I don't know. I'd say they are pretty smart. They do a lot of crazy shit. I have a
Triple
friend.
IIT, let's go.
Yeah.
Huh.
I have a friend who's working on RF communication shit right now, and he's bought a device that's gonna let him receive signals from random satellites.
Damn.
Yeah.
I have only one word, man. Damn. That's it.
DRDO intern in first year, by the way.
No way.
Not like an official intern, but a scientist from DRDO casually hopped on with a professor in our college, and by some chance the interest of my friend and the professor was pretty aligned, so he invited him over to his lab. I wouldn't say it was like a formal internship, it was pretty casual, but just visiting DRDO enough is crazy.
Just made me realize that I'm lacking in a lot of ways, man. I should grind more. I will go now and like try afterwards.
uh,
Crazy.
I really wanna do something similar. I'm talking like I wanna get competent enough by September that I can start approaching professors for the same, like research internships and things of that sort. The thing about research internships is that you have to approach them like months before, because they have to
Oh,
get funds as well. The professors have to arrange funds for you. So if you start approaching them mid September, December, then there's a chance that you will get an internship by summer.
oh, respect. Well, right now my goal is not to go for like research and all that. I just want to compete, man. Like for example, if I learn forward and inverse kinematics, and I can go for like line following robot compressions or like maze solving compressions or something like that.
Yeah.
But that also depends if they conducted this year or not.
For line following robots specifically, I think you need a good grasp of control theory and especially PID. If you might have heard about PID for
Yeah,
line following robots.
yes.
Uh, Currently, I have no idea how to adjust PID parameters, and I tried to do it, but then just left
Oh,
because my patience was short and I didn't want to do things that are considered majduri. So, uh, yeah.
मजदूरी तो नहीं बोलूंगा यार ठीक है.
Come on, it's just adjusting parameters for hours on end.
Kinda true, kinda false, I guess. Like if you get it right on the first try, that's crazy. But yeah, man,
I
like
mean, yes, if
it
you
is time
have,
consuming.
uh, if you know proper control theory, then sure, but I don't know. I mean, for me, control theory is in fifth sem, I guess. So, like all the fundamentals of control theory, I'm gonna learn in fifth sem, and I don't even wanna rush it because I just saw how scary it is and just left.
Oh, Masao is back.
Hello,
Nice name,
Masao.
by the way. Yeah, reminds me of Shinshan, man.
Which one? Oh,
There was a
Masao.
character named Masao, right? In
Yeah,
Shinshan. Crazy.
I think it's the same thing he's referencing.
Yeah,
Yeah,
kinda
yeah,
just.
yeah. It's the same.
Yeah,
It's the
no
same.
way. Why Masao though?
Uh, I just randomly thought about a name that I would like to like use in my new Discord account. And Masao came up in my mind and just used it. Nothing else.
Pretty underrated
Nice, pretty cool, pretty
reference.
cool.
I mean, I remember
So
Masao
what's going
randomly
on?
jumped over alligators in a movie.
Oh yeah, yeah, yeah. The jungle one. Jungle in the नहीं मंगल
Bungle
क्या
Jungle.
था? Exactly.
Bungle in
Yeah,
Jungle.
good movie.
अरे
Yeah,
हाँ वो
like there was a guy with long hairs.
Oh, yeah.
हम्म,
Yeah, pretty good. I almost saw all the movies of Shinchan, I guess. Almost all of them. Not the very
Yeah,
old one, but yeah, new ones I have.
same here.
वो सोया सॉस वाला याद है?
Yes, 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 yeah. टीवी में हुआ था वो. सही था, वो भी अच्छा था.
Okay,
Like the
Masao.
best one, I think the best movie was the one the it was about the circus. What was that?
Uh,
Like Jota or something like that. The it was like it
जादू के
had
पत्ता
Taj.
अपना कमाल दिखा.
Yeah,
अरे
अरे भाई
हाँ
साहब, crazy good movie. Crazy good.
कड़क कड़क कड़क, बहुत कड़क था, मजा आया उसको देख के।
है ना भाई, अच्छा तो था भाई.
Yeah. By the way, Piyush, we are
हम्म
discussing about uh, representing rigid bodies. Yeah. So, uh, just to conclude, we discussed that for describing the position of any 3D object, obviously we need three parameters x, y, z, and the same can be said for its orientation as well. So its angle from the x-axis, the y-axis, and z-axis. So basically, in total, we need six parameters: x, y, z, theta 1, theta 2, theta 3. That's it.
Like we need to get started on like forward and inverse parameters, the coordinates one, like
Yeah.
Cartesian cylindrical coordinates and spherical and
हम्म
articulated one. Like I did try that. Like I gave up at spherical or something. Like third one.
I think it's after this the transformation matrices part, I guess.
Yeah, I did.
Oh yeah,
Till then I just quit.
these pieces of shit made me cry, brother.
True.
Like the position transforms are pretty easy because uh, what transformation matrices essentially are is, as I described earlier, you can just move a frame from position 1 to position 2 using a single matrix. If you multiply this matrix to the frame, then boom, it just moves there to that particular angle, to that particular position. And to transform a matrix by position, you need to multiply the frame by this. This is called a transformation matrix. So this looks like an identity matrix, and this is the distance you want to translate it by, the vector between the 2 points. uh, yeah. Huh, bro? So yeah, let's say we have our frame that we want to move. As discussed, we'll represent the frame in terms of uh, the axis of the frames, like the n-axis, the o-axis, and the a-axis, and
First
then
kinematics programming of robotics. Hello, hello.
yeah.
yeah
Coming. Yeah.
It's
So
fine.
we'll represent the frame by its axis and then its position from the world frame or any reference frame, and then we'll pre-multiply the pure translation matrix with it, and then boom, it just moves there. So you guess you could just memorize this as well. This thing that these things are just gonna be added in here.
Yeah. Man, this is pretty easy, I guess. Like, basically, I into this.
Yeah, like we are just adding in the distance directly.
Yeah.
Like the x, the y, and the z. We are just simply adding them as you would in any normal case. We have just represented that in the form of a matrix so that in case we need to program this in a like in a particular code, then it's gonna make our life easier.
Hmm.
So similarly for rotation we need
Rotation.
for rotation we need three different matrices for rotation about each axis. So one for the x-axis, one for the y-axis, one for the z-axis. Uh,
Uh, Actually, it took me a while, man, for to understand this one. It actually took me a while, man. After that, I just gave up, kinda.
I think I need to. I just need to understand its derivation because that's in research, especially, that is gonna be useful. I don't think I should rely on direct formulas for anything basically.
Yeah.
So, uh, do you guys have your
Honestly,
notebooks or anything?
uh, I have rough notes which are made by my hands, like on a rough board or something like that.
I mean,
My handwriting is
take
not that good.
I'm just gonna take a minute to derive the the rotation matrices on my own in my rough copy or something else,
Yeah,
just to internalize this.
good.
And I think Piyush, it might be a bit hard to digest everything at once, so you could take the time just going through the book if you don't mind.
Uh,
Actually,
the
yes,
one
man. Like,
you shared,
if
right?
you read, if you read the book, it's pretty good actually. Like, if you saw
Yeah,
the oceans and read it, you'll understand it way better, man.
yep.
Really better.
You could directly go to chapter 2,
Yeah,
kinematics.
actually, do that. Don't read the first chapter. Like, it's all theory. Which is not that important. I
Yeah,
just say chapter two is the main one. Like, that's the start of everything.
yeah. Just skim through it. If you find anything that feels hard, then just spend a lot more time in that.
I would say conclusion in this or starting the course I discussed, like I shared, let me check if I have it right now.
Hello.
Yeah,
Yeah.
Sandeep, did you see what 8-bit posted?
Uh, I mean, if 8-bit posted something, it must be crazy. Wait, is it this one?
Yeah.
Bro, I need to
Just
download this
speedrunning
video.
your project.
Wait, how? Has all the files been uploaded yet?
No, he created the remaining files by himself.
Huh?
Yeah,
What?
he created everything like from
No
scratch.
way. No way.
Yeah, he did. He did.
Or maybe he used a steel for them, like from the repository
Uh,
for. Like,
yeah, he
no way.
used them for like a reference, but
Like,
he created every bit from scratch, like
no
how we
way
were supposed to
actually
create.
made all the holes the for aligning shit. Wait, no.
Yeah, he
Come
did.
on.
Yeah, he did.
What the fuck? What the fuck? I finished making the individual comments there.
लाइक उसके कान में बस एक ही म्यूजिक बजता रहेगा डू 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 डू
Illuminati.
ड्रीम का स्पीड रनिंग म्यूजिक भाई
Did you know that 8-bit is actually Indian as well?
Oh,
Yeah, I think his real
या
name.
हिज नेम इज साहिल राइट
Yeah, I could have never
आई
guessed. Like,
सॉ इट या हिज वॉइस इज लाइक प्रॉपर नॉट इंडियन
yeah.
racism at its peak.
I mean, I guess his like previous generations like were settled in like abroad, so
Racism
I
at
don't
its
know.
peak. I think he's studying somewhere in Ohio or New York.
Ouch. Jealous, man. Jealousy.
Same here, same here. I wanna go abroad someday.
Not someday. You have 2 years to prepare for it, man. All the best.
Yeah.
Yeah, 3 years. No, okay, yeah, 2 years. Yeah.
2 years, yeah.
Did you know that?
Like you can go. Yeah.
Yeah.
No, it actually is 3 years. Huh.
Did
Oh
you know
yeah,
that?
three, yeah.
Did you know that the only person who like supported me, supported my idea of going abroad was actually a member from Pakistan.
Did he
And
invite you to Pakistan or something? Like, yeah,
no,
let's go, guys.
it's a member from our own community, and it's a very sweet member. I'm not gonna name them because don't have the consent.
Hey, I should say,
Yeah,
yeah,
okay,
I
okay.
have to say, racism at its peak again.
No, wait. It's anti-racism. It does not count. Okay.
Okay, okay.
Yeah.
Anti-racism. Nice. New thing.
Yeah.
Crazy.
Yeah, Sandeep,
Like,
are you
if you,
streaming right now?
Yeah, I am streaming right now. I don't care. Call me Pakistan
Yeah,
content.
okay.
Call me anti-national, I guess.
I'm actually confused in like choosing RL Norton's like Intro to Robotics or its course or this one which I shared in
I
Intermediate
mean,
Mega Thread.
Saeed Biniko is probably better. I mean, R.L. Norton is a very good author, but R.L. Norton is someone that's entirely focused on the mechanical side of robotics.
yeah, honestly, I read the both of them. Like, I read both introduction. Like, I did follow like 2 chapters of both of them, and I would suggest like do introduction to robotics one.
Yeah,
It's better.
Saeed is better.
But
Uh,
in the sense, like
what
you can understand it. Like the maths is easy.
what about this?
Which one? R.L. Norton, right?
Uh,
No, replied to my message. Uh, uh, it's not some famous professor or something, but
What modern robotics by
it's
Linkin
an
Park?
resource list intermediate mega thread.
I have no idea. I'm not sure about this. Prof. Lucy could be good, maybe. Wait, what book is he following though?
damn, but this is actually is pretty good.
Could be a great
I think
review.
he's following this one. Yeah, I think he's following the introduction to robotics book, I guess. It's like that's the
I mean, all I would need is one diagram and it would be pretty clear. Oh, yeah. He's definitely using Said. This
yeah.
exact
No,
diagram is
if
in
he
Said.
yeah, I guess. Oh, actually, I would suggest to watch this rather than reading.
Yeah. This is a
Damn, good
cool
find, brother.
resource. Good find, yeah.
Yeah,
I
good
mean,
find, mate.
damn, even small channel. That's good. Subscribe to him.
Support him. Let's go.
Subscribe.
Wait, Isto, what are you doing right now?
Jobless, unemployed.
No, means what did you do? What study? Like engineering?
Oh, actually, I mean, like my first is yet to begin. I will go in first this year.
Oh,
I'm a kid,
okay.
man. Not even 18 plus.
Damn, this kid.
Expected reaction. Like this
ये
is
चल
scene.
मुझे सुनाई नहीं दिया ये क्या था
Yeah.
अरे
नो
वो बच्चे
डिसीजन
का मीम
माइंड नो
नहीं क्या? नहीं, बच्चे का मीम लगा तो नहीं क्या? हाँ, अभी बहुत लेट हो गया भाई। बहुत लेट हो गया।
अरे नहीं
बहुत
हाँ 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 वो वो
हाँ
जेई वाला भाई वो जेई
Jay.
वाला
हाँ हाँ
अरे शिट यार काश अब किंडर ये क्या बोलते हैं आपको
Tinder.
किंडर गार्डन से प्रिपेयर करना चाहिए था हो जाता फिर
हाँ।
आपका आप 2 साल लेट हो जाए
Definitely.
क्रेजी
नाइस ब्रो। It's it's nice to hear that people are liking this field.
No, actually, I was very interested in this one. I don't know why I gave Jane and all that. I should like go for like diploma or something and like compete in competitions and all that.
या ब्रो,
I
एक
mean,
मेरा दोस्त है, उसने भी डिप्लोमा किया है। आई मीन तेरे को अगर
Like
बाहर जाना है, लाइक फिर हायर प्लेटफॉर्म्स पे जाना है, तेरे को इंजीनियरिंग करना ही पड़ेगा। लेकिन
uh
yeah, for
अगर
higher studies you
स्टार्टिंग,
need engineering.
लेकिन तूने 11th 12th किया होगा ना? हाँ,
yes yes
11th 12th किया होगा ना? हाँ, फिर अभी
yes.
फायदा नहीं है डिप्लोमा करके।
नहीं नहीं अब नहीं करूंगा भाई मैं सोच रहा था वो
हाँ
ना 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 ना
हाँ।
अब 6 साल ही डालूंगा खत्म 2 साल अच्छे से उड़ा दिए मैंने वैसे ये एक्चुअली बहुत अच्छा फाइंड है लाइक इट कवर्स एवरीथिंग
Yeah.
मैंने कब का भेज के रखा था, वो खुद को पता नहीं था। मैं वही चालू करने वाला था, लाइक सुबह उठ के 6 बजे। ये मेरा डिसाइड नहीं हुआ था अब तक तो।
Oh, actually, like if you are speedrunning this, to be honest, it's a good thing. You can speedrun this. Like,
Yeah.
but the thing is, you will not remember a thing after a week or so.
That's the main
I'll
issue with
write it down.
videos.
Yeah,
वो भी
like you
है।
will understand it all that. After a while, you will just forget it, man.
It
जेई में
gave
बहुत
it
किया था मैंने.
pseudo confidence.
Yeah, same man.
Physics
Like
वाला.
हाँ, अगर आप नोट्स बना के कर रहे हो तो हाँ भाई बहुत अच्छा है. फिर सही है.
हाँ भाई, नोट्स बना के ही करूंगा भाई।
Yes. ठीक है भाई, मैं भी करूँगा फिर.
Yeah.
मैं सुबह 6 बजे चालू करूंगा। लाइक अभी
नहीं
तो नहीं
भाई,
करूंगा।
इतना इतना जल्दी
कल
नहीं
तो
उठ
जाना है
सकता
मेरे
भाई
को।
मैं.
5:30,
इतना जल्दी नहीं
5:30.
उठता हूँ भाई.
भाई
फाइव
संदीप से तो
थर्टी
कुछ सीख ले भाई।
ओ माय गॉड भाई मैं 7 8 बजे उठ रहा हूँ आजकल. अरे
I'll
जेई
pick
के
up at
टाइम में
5.
बहुत जल्दी भाई देख. Like when I was giving JEE, at that time I was waking up like at 4 or something. Sleep at 12, wake up at 4. Life of
Bro,
a addict man. Even then, didn't got a good story, man.
enough procrastinating. Let me do the derivation.
Yeah.
ये
And food.
Sandeep, if you're done with the things, sent you a book of optimization techniques on your direct messages. Like if it direct messages, if it aligns
Yeah,
with your syllabus, you can. That's what my professor is using too. So
let me just go through the contents.
yeah,
Yeah, we haven't explored any books, so might be good. Example, engineering optimization. Okay.
One addition of it physically. Uh,
Okay.
Third in large.
Yeah, this is relevant. Inequality constraints. Uh, yeah. Damn, this book is very detailed. Detailed would be the right word. Geometric programming. I guess I need to find the exact thing that I need for the paper, and then I can probably get into this. This is something
Yeah,
that's very important in robotics. Some optimization. And
check your
even,
syllabus and then we can figure out
yeah,
which topics to cover for now.
from a robotics perspective, optimization of fuzzy systems and particle sound optimization are probably the most important things in this book.
Optimization of fuzzy system.
Sorry. Particle aspects of, yeah, this is important as well. Multi-objective optimization. The only thing that I'll need to watch out for is not getting too much into the details, because let's be real, this book is pretty big.
Yeah, it's in large.
Oh, oh, I finally figured out the derivation of it, man. Finally.
Which one?
Took me the one you're trying to solve.
Oh, oh shit, I've been procrastinating.
Like, which, yeah, it's pretty much it. Like, if you draw it by hand, you will get it.
Yeah, PNOA. So n is not going to change, so px is equal to pn. And then I need to find py. Find py, and py is sometimes dz is this. Uh, This is theta as well. Theta as well. Then z.
चलो भाई मेरे सुनने का
So L2 is equal to PA sin theta, and L1 is
नहीं जो फॉलो कर रहा ना
L1 is P naught PO cos theta. So Py is PO cos theta minus PA sin theta. And for PZ is this line. So PZ itself is hints L3 L4 okay
तो हुआ क्या आपका?
not yet
Hmm.
PXP
लाइक आपको ना, आपको मैं हिंट दूं, काइंड ऑफ
for PZ yes
PZ ये चैन डायग्राम देखने का PZ
let me
सो
try
ठीक है,
like
जो आप डायग्राम देख रहे हो ना, ठीक है, जो L3 का है, L3 को बेस समझना, वो ट्राइंगल था बेसिकली, जो रेक्टेंगल है उसके ऊपर जो ट्राइंगल है ना उसको देखो आप।
yeah
तो बेसिकली L3 को बेस लेना और PO को वो स्ट्रेट लाइन लेना, एंड फिर आप थीटा देखोगे ना तो हो जाएगा, देखो
PZ L3
लाइक उसको एक
L4
सेपरेट डायग्राम में आते देखो, आपको इजीली हो जाए, इजीली हो जाएगा।
mm, oh uh, P and PAPO. Uh, with the P naught sine theta. P naught P naught P naught sine theta. Oh, 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 oh. Got it. Got it. Got it. Got it.
Nice.
So L3 is P naught sine theta.
And also written in the convention.
And then L4 is er, 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 er.
मतलब आपका खाना हो गया?
Hmm?
खाना भाई?
Ana? Dinner?
खाना खा लिया?
Yeah, done.
Nice.
This is PA. This is theta. And PA. PA cos theta. So PZ is just PA sine theta plus PA cos theta, right? Boom. Nice. Then in matrix form, Px, Py, Pz is equal to uh, 0, 1, 0, 0, P and OA, and 0 cos theta minus sin theta, and then 0 sin theta cos theta. Done. This is rotation matrix for rotating orbits. Nice. Rotational matrices. Okay, so we have covered this. What I want to try is deriving the same for y and z as well, but I'm just
न-
gonna sleep now and deal with it
नहीं,
tomorrow.
एक्चुअली आपको ये डराइव करने की जरूरत नहीं पड़ेगी। मतलब आप तो इजिली बताओ ना। मैं तो
Hmm.
जो हमने ऊपर किया था, देखो P इज इक्वल टू एच वाई जेड, लाइक एक सिंगल मैट्रिक्स लाइन वाला नीचे 1 into 3 वाला मैट्रिक्स था, देखो।
Uh, this one?
नॉट दिस वन, जो एकदम से इनिशियली हमने देखो ना, बहुत स्टार्टिंग में हमने किया था P इज इक्वल टू एच वाई जेड, एंड उसके बाद हमने उसको थोड़ा सा कॉम्प्लिकेट किया था। फिर हमने उसको किया था फ्रेम के रिलेटेड, F इज इक्वल टू
अच्छा, for the vector.
हाँ हाँ हाँ। तो जैसे जैसे तो देखो, तो इनिशियली हमारा इसमें जो फर्स्ट वाला है ना, रोटेशन रिलेटिव टू एच वाला, मतलब जहाँ पे एच कांस्टेंट रह रहा है एंड बाकी सारा थीटा रोटेट हो रहा है। या this one, yeah. AH, BY and CZ, this one. So basically जब हम रोटेशन के लिए बारे में भी जब सोचोगे ना, तो जो कांस्टेंट है वो बन रहेगा, ठीक है। तो फिर जो, इसलिए अब रोटेशन वाला छोड़ना, मैं आपको इजी बता पाऊंगा फिर।
आई मीन जस्ट याद करने के लिए आई गेस इट्स फाइन, मैंने वैसे याद किया आई
हाँ,
गेस तो।
काइंड लाइक वही, काइंड ऑफ वही है, मतलब लाइक वो सिंपलर वे में याद हो जाए आपको। तो
हाँ
लाइक जो कांस्टेंट है, जैसे कि,
या
ठीक
जो
है।
कांस्टेंट है उस वो बेसिकली उस पर डील नहीं कर रहे, एंड देन जो मूव हो रहा है उसमें
हाँ
कॉस थीटा साइन थीटा द सेम थिंग,
हाँ हाँ
and then
हाँ।
for same thing for y, but these move, but this matrix remains, this matrix remains. So just याद करने के point of view से it's fine, but
हम्म।
I just wanna do it just for practice in case I'm met
नाइस
with a
नाइस।
problem that requires me to do this sort of thing.
सही सही है।
Yeah. बाकी का सुबह
ठीक
साढ़े
है। हाँ।
छः
ठीक है ठीक है। मैं ट्राई करना होता है, जल्दी उठने का, देखता है।
ओके।
होप सोच जाऊं। हाँ। ठीक है, गुड नाइट भाई।
क्या मैं डायरेक्टली इसको डाल दूँ एक और इवेंट, या फिर बाद में सोचूँ?
चलेगा।
बिकॉज आई एम नॉट श्योर कि मैं सुबह ये करूँगा या फिर एक्चुअली बहुत काम है सुबह, ये भी करना है, एंड देन
हाँ।
डिज़ाइन ऑफ मशीनरी, देन कॉलेज पे पढ़ाई, AMFT इलेक्ट्रोमैग्नेटिक फील्ड
डैम।
थ्योरी, नो आइडिया।
सही सही है।
ओके मे बी
ठीक है, देखता है।
कल
हम्म।
सेम टाइम पे रात को एक बेटर
हाँ,
रहेगा।
चलेगा।
राइट,
8:30 राइट।
8:30।
ठीक है, चलेगा।
बाय बाय, गुड नाइट।
गुड नाइट गुड नाइट।